All right, so molecules that are polar can interact with each other. This is what gives water its ability to bead up. It has a surface tension. It sticks to glass. It sticks to things. It makes it quote unquote wet. There are other liquids that are not wet because they don't have what we call intermolecular forces. And intermolecular forces are attractive forces that exist between neighboring molecules or ionic compounds. They are much weaker than covalent bonds and ionic bonds, but nevertheless are extremely important forces of nature. There are three main types of intermolecular forces. I don't know why your book includes the ionic bonds, but I'm not going to go over it. We've already talked about how ionic bonds work, so I'm not going to rehash old news here. But the three types of intermolecular forces are dipole-dipole attractions, hydrogen bonds, and dispersion forces. Dipole-dipole attractions occur when two polar molecules interact with each other. They will align in such a way so that their oppositely charged poles are next to each other. And this is what a dipole-dipole attraction looks like. So we have the partially negatively charged chlorine atoms on the right side in each molecule. We have the partially positive hydrogen atoms on the left. And so what you get is the partially negative chlorine of one molecule facing the partial positive hydrogen atom on the other. Opposite charges attract. The second type of intermolecular force is a hydrogen bond. And a hydrogen bond exists in molecules that contain either nitrogen, oxygen, fluorine, and chlorine, and they also have a partially positively charged hydrogen atom, meaning that hydrogen atom is bonded to one of these atoms here. Lone pairs of electrons on the highly electronegative elements form an H bond to the electron-deficient hydrogen atom. And so you can see that right here. This is ammonia. You have a partially negatively charged nitrogen atom, and you have the partially positively charged hydrogen atom bonded to that nitrogen. Ammonia has a lone pair on the nitrogen. Here's my terrible Lewis structure of it. Here's the wedge. Here's the dash. Okay. The nitrogen in its native state has 5 electrons because it's 1s2, 2s2, 2p3. The hydrogen is just 1s1. There's 3 of those, and you've got 2 plus 3 is 5 for a total of 8 electrons. And you've got 2, 4, 6, and 8 electrons in total in that molecule. So you have a lone pair there. Trigonal pyramidal is the shape. Okay, just kind of rehashing all of that. Electronegativity of nitrogen is 3.0 and hydrogen is 2.1. Okay, so there's a lone pair on this nitrogen that I'm going to put in blue here. And that is attracting this hydrogen because the hydrogen is partially positive. It is hydrogen bonds that is responsible for the fact that ice is less dense than liquid water. Ice floats to the top. And actually, if this didn't happen, if ice was more dense than liquid water, most substances, by the way, are more dense as a solid than as a liquid. The atoms just get closer and closer together as it cools down more. But if that was the case for water and not what we really have, which is due to hydrogen bonding, we probably wouldn't have life on Earth. Parts of Earth would be cold enough to freeze, and the water would freeze from the bottom and up, whereas right now, the coldest part is going to freeze at the top, and it's just going to sit there, and it's not going to go anywhere else. And that top layer of ice actually insulates the water below it, keeping the water that's not on the surface from freezing. And so hydrogen bonding keeps life in the aquatic realm, which obviously led to life on the terrestrial part of Earth. But there's many things that hydrogen bonding is responsible for, and you just wouldn't have life as we know it without hydrogen bonding. Hydrogen bonding is also stronger than dipole-dipole interactions. It's the strongest intermolecular force. Here's some more examples of hydrogen bonding. We have water, and we have hydrogen fluoride. The last type of intermolecular force is dispersion forces. These are temporary induced dipole moments in otherwise nonpolar molecules. And these temporary dipole moments will force molecules to interact with each other, much like dipole-dipole interactions, although much more weakly and for a much shorter time period. They can occur due to random placements of electrons or from collisions. So if two atoms or molecules come together and they collide, one might be polar in a sense and the other one's nonpolar. Because let me actually draw this. If I have hydrogen chloride, HCl, which is a polar molecule, you have a partial negative there, a partial positive there. If that's colliding with nitrogen, which has a triple bond there, the negative charges on the chlorine, or the partial negative charge, is going to force electrons away from that nitrogen that it actually collides with. So what you get would look like this. The result would be the atom on the right would be slightly larger, at least with its electron cloud, than the atom on the left. So you'd get this partial negative charge there, the partial positive charge on the left, but this is all just temporary. The moment those molecules go away, the charges will eventually equilibrate or distribute themselves equally between both nitrogen atoms. This picture here shows you just the temporary dipole moments that are created in dispersion forces due to just movement of electrons, not due to collisions. But as you can see on the picture on the left, the 3 electrons are evenly distributed around the nucleus, but the atom on the right has an unequal distribution, or an unsymmetrical or asymmetrical distribution of its 3 electrons. So the nucleus is right there. You have this atom right there. These 3 electrons are going to be attracted to that nucleus, which is on the surface of it, and so you can see it's been forced that way. You have partial positive, partial negative next to the other molecules, partial positive and partial negative. This happens billions of times every second, so it's like they're very temporary, and they're very weak. The dispersion forces are the weakest of all of the intermolecular forces. And so you can see in this table we have types of intermolecular forces, and including ionic bonds and the strength of them, and some examples. So ionic bonds would be the strongest intermolecular forces if you include them. And I'm going to exclude covalent bonds from this list. I don't want this to confuse you, because covalent bonds are stronger than ionic bonds, much stronger. I don't know why they put that there. That's an error. But hydrogen bonds are the next strongest intermolecular force. Dipole-dipole interactions are intermediary, and dispersion forces are the weakest. Some examples of melting points for certain types of intermolecular forces: magnesium fluoride, an ionic compound, has a melting point of 1,248 degrees Celsius. Sodium chloride is 801. Water is 0 for its melting point. Ammonia is negative 78. Those two are hydrogen bonds. They have hydrogen bonds. Basically, the hydrogen bonds make all of the different molecules of water stick to each other. So in order to melt it from a solid, you have to break apart that glue, so to speak, in order to get it to melt. And then if you want it to boil it, it still has hydrogen bonds occurring. You have to break apart those in order to get it to boil, because gas particles don't interact with each other. Hydrogen iodide, which only has dipole-dipole interactions, is negative 51. HBr is negative 89. HCl negative 115. Dispersion forces, you have bromine. These are nonpolar molecules. Bromine has negative 7, chlorine negative 101, and fluorine negative 220. In today's lecture, we talked about bent molecules, dipole-dipole attractions, dispersion forces, hydrogen bonds, linear triatomic molecules, nonpolar molecules, polar molecules, tetrahedral arrangements in the VSEPR theory, trigonal planar, trigonal pyramidal, and the valence shell electron pair repulsion, or VSEPR theory.